And once I have the confirmation that it's streaming, I can close that screen. So that is going. Close that. All right. And let me put Discord back into my view so I can actually see text messages. All right, so we are 36 seconds past the start time of this class. So I'm going to get started here. So what we'll do today is the first thing is to talk about the prologue cousins homework assignment. This one is kind of a continuation of what we talked about last time. So just as a very quick introduction to this, I can show you what the questions are about. So basically, in the end, we want to be able to implement a program in Prolog where it can find or confirm cousinhood. Okay, so basically you specify a family tree using the parent of predicates as facts, and then what we'll do is we'll try to write predicates so that the final predicate can confirm cousinhood. So we're not just talking about usual regular first cousins. So we want to generalize this so that we can handle nth cousin r time removed. So the rules are pretty clear. Last time, if you go back to the text channel from last time, we talked about the technical terms of cousins. So when we say first cousin, so those would be the people of the same level as we are, except we share a grandparent in this case. So second cousins would be people where we share a grandparent and no lower ancestors should be shared. So that's why siblings are not considered first or second cousins, even though siblings definitely share the same grandpa and the grandpa and so on. All right, so I'm looking at the text channel. Can I share my screen? Oh, right, I forgot about that. All right, so let me share the screen on Discord. Not that there's really a whole lot to share at this point, but yes, I forgot. All right, so here we have the prologue cousin homework assignment, and it's divided into steps. So instead of just throwing everything out as one single gigantic program that you have to undertake, it is broken up into smaller steps. And I am looking for my mic setup thing because I think the gain is too much. So let me just kind of change the gain a little bit. Alright, so I think that's better. Yep. Alright, so there we go. And let me close this first. There we go. And I have to reopen my Discord screen. There we go. Alright. So are there any questions about what we want to do? Are there any questions about who is a second cousin, or what is a fourth cousin twice removed, or terminology like that? I'm looking at the text channel and it seems pretty quiet. Okay. All right, so here's an example. This is the family tree of the Simpsons. All right, so what we can do is to focus on this guy over here and this girl over here. Okay, so there we go. So you can see they're related because Bart is the son of Homer. Homer is the son of Abraham. Abraham is the son of Orville. And then Orville is the son of Otut. Otut is also the father of, okay, we have to go up one more. So Ohud is the son of Howland. Howland is the father of Lou. Lou is the father of Twyla. Twyla is the mom of Furnace, I guess. Not very good at pronunciation of these names. So, and Furnace is the mom of Pomona. Pomona is the mom of Hazel and Violet, and also Alberta. Okay, so the question is, we know Hazel is a cousin of Bart. The question is, what is the degree of cousin in this case? So I'm gonna let you guys think about it a little bit. Too many. So you basically have to count, and find out, at which point they have a shared ancestor, and then the number of parent links to get to the common ancestor minus 1 is going to be the if of the cousinhood. So let's do some counting here. So here's Bart. 1 goes to Homer, 2 goes to Abraham, 3 goes to Orville, and then 4 goes to Old Tut, and then 5 goes to Howland. So they are 4th cousins. Hazel and Bart are 4th cousins in this case. So I see Armand is typing. Because first cousins share a grandparent, not a parent. That's why. You can sort of call your siblings a zeroth cousin, but that would be pretty odd, right? We don't call our siblings zeroth cousins. So when people refer to first cousins, they refer to people who share a common grandparent. Unless I'm wrong, right? Because that's my understanding. So if you look up, first cousin, and it was right there. Okay, it was just right where the search page was listing. Okay, FIRST. There we go. So first cousins share a grandparent, so it's 2 generations. So that's why the if here, the th of your cousin is the number of generations minus 1. Number of generations until you get to the common ancestor. Yeah, father, mother, doesn't really matter. So we are not putting gender is not put into play in this particular program. We only care about parent of, so there's no gender identification. So are we good so far? Any questions about the terminology of what is a 4th cousin? Yes, that website is certainly helpful. So now when we talk about removed, that means they're not at the same level. So here's Bart, and here is Pomona. So Bart and Pomona can be seen as cousins. So they would be 4th cousins once removed. That is how you can call them, because they are not at the same level of the tree, and yet they share the same ancestor. At some point in the tree. So I believe that is also explained in the page that I linked to. That's actually I linked to that site, the very same web page from the text channel on Monday as well. All right, so that's basically what you're going to do, is basically to implement the logic of confirming cousinhood. So but it's separated into steps. So question 1, is only the first step, and this one only wants to specify a predicate to confirm ancestry, also specify a rule to confirm siblinghood. Specifically, ancestor of xy should be true if and only if x is an ancestor of y. I believe that was already done for you, so you just have to kind of go back to my notes and locate that. And then the next one, says, it's a little bit more specific. It is ancestor of, okay, let me take it back. Ancestor and of. Okay, so one is kind of like string copy. The other one is string and copy. So this one does put an extra constraint of, we need it to be this many generations. So X is an ancestor of Y, but we only care about whether X is a nth generation ancestor of Y. So that's going to be it will come in handy later on. And then question number 3 expands this a little bit more. So this time we want a predicate called ancestry x, y, and m, where x and y are people, and then n and m are numbers. So we want to find an ancestor, and we want to find a common ancestor. The common ancestor needs to be n generations away from x, and that person needs to be m generations away from y. So that's what ancestry x, y, and m is about. But there's one little extra thing that we want to make sure is they do not share an ancestor prior to n generations away from x or m generations from y. So we cannot just say, oh, okay, since x and y are siblings, they also share a grandparent and share a grand-grandparent. No, that doesn't work. Okay, we want actual, we do not want the ancestry to start too early. We want the common ancestry to start at n generations away from x and m generations from y. So you're going to have to use negation in this case because you need to negate certain things. And it might be helpful to create another predicate that will locate ancestry, even if it will confirm ancestry regardless of whether there's an earlier ancestor or not, because you need that to negate things. And then the last one is the actual cousinhood. So when we specify the cousinhood, we have this particular predicate here. It is simply called cousin. It has got x, y. X is a person, y is a person. N is the ith, of the cousin. So first cousin would have n being 1. Second cousin would have n being 2, and so on. And then R is the number of times removed. So if it is a regular cousin, R would be 0 because they would be at the same generation. And you can also specify R being 1 if you want to specify once removed, and R can be 2 if you want to specify 2 removed. And then there's some extra constraints here. N should be at least 1 because we don't want to talk about 0th cousin. Those would be actually just siblings, but we just make it a rule and say cousins cannot be 0th cousins. And we also have this rule that R has to be less than n and R has to be non-negative as integers. So those are the extra constraints. And then for each step, I want you to turn in an entire program. So this way, it gives you a chance to kind of move on from one to another project. Unless you really want to install SWI Prolog on your own computer, which can be done. I mean, it's an open source program and you can certainly install it on your own computer. But I thought it's much easier if you were to go to the SWISH, the Swish website, and just go ahead and sign in. I would recommend you guys signing in because if you sign in, then you can actually save your program on their site. And I'll show you what you need to do when you save your program. So you go to File and you click on Save. So the first thing you want to do is to uncheck Public because you don't want other people to be able to see your project. Not so much for security purposes, but it's more like for academic integrity purposes. So you can give it a name, give it a title, and then you can just go ahead and save the notebook. So a notebook is nice in this case because a notebook can have multiple programs. So within the same notebook, if you hover your mouse pointer to about here, it will allow you to create a new program. So basically, you can just create new programs, and then for each program, you can just kind of copy and paste the entire content from the previous one. So this way, you can build your program step by step and not lose track of the programs that you have done prior to a particular step. So that's kind of how the assignment is set up. and I have not released it yet, so I'm going to release it now. I'll give you guys a week to get this done. I think if you really kind of start working on it as soon as possible, it should not take too long. And also you can ask questions in class, also during my office hour, if you have any questions. Alright, so I'm going to release it. You guys have 1 week to complete this. Today is the 1st, so it's going to be the 8th when this is due. And it's going to be due right before class, which is kind of the convention that I usually use. There we go. Save and publish, and now you have access to your prologue homework assignment. So do we have any questions about the homework before we resume our discussion on recursion? Alright, that does not seem to be the case. Well, in that case, we're going to resume our discussion on the recursion. I do have my Joplin, kind of ready for today. So let me make it slightly bigger by removing the panes that are not needed. So we just talked about the prologue homework assignment. And once again, if you have any questions, just go ahead and ping me, and I'll see what I can do. Okay, most of the time you probably want to experiment with prologue a little bit. There are certain examples also included in the lab or in the instructions, so you can actually just go ahead and try some of those examples, and then gain an understanding of how prologue works. So we're now getting back to recursion. So recursion is a technique where we recognize self-similar stuff. And when I talk about self-similar stuff, we can talk about structures. We can also talk about problems. So we'll start with structures. In nature, okay, this is not necessarily trees in programming, but in nature, trees are self-similar structures. In other words, if you look at a large branch, it has smaller branches. When you look at a medium branch out of a large branch, the medium branch also has branches. When you look at a small branch, it also has branches. So it goes all the way to a leaf. Okay, so when you get to a leaf, which is also a technical term to refer to a node in a graph, where it does not go to any more vertices. So when you get to a leaf, then it doesn't have any more branches. So that's kind of a special case of a branch, of a node, or of a vertex that has no outgoing edges. So that's a self-similar structure. Folders, okay, because we are all familiar with folders on a computer, and folders are self-similar. In other words, the root folder, okay, and I assume most people are using Windows, so your root folder in Windows is C:, and then followed by a backslash. That contains a bunch of subfolders. If you look into the user's subfolder, it would have its own subfolders, one for each user on your system. When you go to the subfolder of one particular user, it would also have subfolders. Okay, typically one subfolder would be documents, one subfolder would be downloads, one subfolder would be app data, which is usually hidden, and so on. So we are really quite familiar with self-similar structures, just from daily life and also from the use of computers in general. But I also claim that arrays are also self-similar structures. Especially in C and C++, because if you look at arrays in C and C++, an array is no more than just a pointer to some place, okay? And then you can apply the index operator, the square brackets, once you have a pointer to somewhere. So that makes arrays, kind of inherently a self-similar structure. When you look at an array of, say 5 items, okay, you can say, oh, okay, I'm taking the first item out, but if I advance the pointer to the next one, that becomes its own array of, guess what, 4 items. When you look at the array of 4 items, you can say, okay, I'm going to take away the first item, and then the rest, the other 3 items, can be also seen as a sub-array. So that's one kind of interesting way to look at arrays, especially in C and C++, because in Java you cannot do that. In Java, or in most of the scripting languages, you cannot just say, oh, I'm just going to move the pointer along and look at what the pointer is pointing to as an array that has one fewer elements. That doesn't work because most other languages do not have pointers. Do we have any questions at this point about self-similar structures? Okay. Anyone else? Okay, all right. So given that we may not have any problems with recognizing self-similar structures, there are problems that are also, self-similar in nature. So this is an interesting one. Okay, this is a classic one. Okay, a classic example is to search in a binary search tree. Merge sort is not exactly relying on self-similarity. At least not the merge sort that I typically use, because it basically is just an iteration between splitting and merging, and then splitting and merging. There are two main ways of implementing merge sort. One way is to do it recursively, and the other way is to treat each is to look at the entire thing as a stream. So you have one income stream, to start with, and then you would split it into two output streams, and then you would merge the two output streams back into one, and then split it again. So the stream method of looking at merge sort makes a whole lot more sense compared to the recursive way of looking at merge sort. I'm trying to think of how to explain why it makes more sense. Yeah, so you can do it through recursion. Okay, so let me kind of give you a backdrop of how merge sort came about and what is the significance of merge sort. So imagine you're back in the 60s. So that's when your parents were born, possibly your grandparents. And computers back in those days do not really have a whole lot of RAM. Okay, RAM was very expensive, so most of the data would be stored on tapes, which is a really foreign concept to you guys, right? Who would put any type of content on tape? Well, back then, people do, because that's the most inexpensive way to store a massive amount of data. So imagine now you have a tape, okay, that contains a whole bunch of records. Can be student records, can be tax records, or whatever. It doesn't matter. But it's not sorted by the thing that you want to sort it with. Okay, so maybe it's just maybe it's just sorted by the order of these records coming in. Maybe it's sorted by some other thing, but it's not what you want. Okay, so let's just say that you want to sort it by tax ID. Okay, these are tax records. You want to sort it by tax ID. So now you have the entire population of the United States back in the 60s. I know it's not nearly as many as we have now, but it's still a pretty sizable number. And the amount of RAM in your processor, on your computer, the mainframe, can store maybe 3 records. That's it, okay? So you can't really load the entire thing in and then put it into an array and then apply Iraj, recursive algorithm. That simply won't cut it with it. So what do? Well, we're going to use tapes. So it has one tape that we start with one tape, and that tape has the unsorted records, and then what we need are 2 additional tapes. So initially, the one tape that we are given with is going to split into the 2 tapes, as quote unquote the spare tapes, and then that split excuse me. So that split will identify runs, right? Basically, short bursts of records where things are in order. So when we will send one run to one tape, and then the next one we'll send to the other tape, and then the next one we'll send to the first tape again, and then so basically we just alternate between the 2 tapes when we identify these quote-unquote runs of records. So now you have these, and then once you exhaust all the records from the one input tape, then you have the 2 tapes containing exactly the same records, but they are on 2 separate tapes, and each one has runs. So then you have the merge operation. So what the merge operation is doing is it's flipping the two tapes around. So the two output tapes become the two input tapes. And then what you do is you look at the runs, the current run on each tape, and go like, okay, so we can take one from here, we can take one from the other one. So the idea is we want to merge and basically increase the length of the runs and reduce the number of runs. So now once you merge, you are usually having the number of runs, and then you have all the records in one tape again. So this one tape now has all the same records, but the number of runs would be 1/2 of what it used to have, and then you split it again, and then you merge it again, and then you split it again, and then you merge it again until you have one single run left. Then you're done. So that was the origin of merge sort, okay? Because the whole idea is your mainframe computer doesn't even need a whole lot of RAM, okay? It just needs enough RAM to store the program itself and 2 records. That's all, okay? Because once you can store 2 records, you can look ahead enough to figure out, okay, are we continuing a run? Should we take this record from this tape instead of the other tape to make the run longer, and so on and so forth. So that was the origin of merge sort. Merge sort, I think, was never meant to be used in memory, used with sorting in memory, even though the time complexity would still be the same, which is n log n. The best part about merge sort is it basically uses streams. So there we go. And you can do the same thing even if you use arrays, and there's an advantage of using this approach as opposed to Iraj's recursive approach to do merge sort. So the approach of treating an array as a stream, which means you basically just move from one record to the next, to the next, to the next. The nice thing is you have locality. And locality is actually extremely important when we are talking about modern memory architecture, namely, the DDR architecture, the double data rate architecture. Because double data rate architecture shines when you are not only accessing a few bytes, but you're accessing a block in a sequential manner. And merge sort, if you implement it non-recursively and looking at the array as a stream of records, it is extremely sequential. You only go in one direction, and you're always just putting a record right after the other one. So as a result, the efficiency is also extremely good as well when you are combining this technique with the DDR memory architecture, because DDR with the burst fetch and the burst write, and also the caching mechanism in the processor, is basically designed to handle stuff like this, basically reading and writing with a lot of locality. And that's why merge sort is actually interesting in a way that, it has the same time complexity as quicksort and many of the other quote-unquote efficient sorting algorithms. But if you exploit the memory architecture, the DDR technology of memory architecture, merge sort probably can beat the other sorting algorithms in terms of just a constant time. So we are not talking about changing the time complexity. It will still be the same tight bound, which is n log n. But when you look at the actual constant, okay, the coefficient of n log n, I think merge sort can potentially have a very small coefficient. All right, so I might type something in the text channel. All right, so let me take a, I have to move it because I'm missing the end of the other part. There we go. All right, so if you are doing by starting with smallest runs on a large unsorted list on the first tape, it would seem a bit inefficient because you can't rely on solid patterns emerging from randomness. Not exactly sure what you are referring to. But merge sort starts with small fragments. Each run is usually pretty small initially, and then we just make those runs longer and longer as we go. But when you're doing this with a tape or with a stream, everything is just moving in one direction. So there's not a whole lot of back and forth, because you're just deciding, okay, I'm reading the next record in, which output tape should I append it to? So you're still appending. It's just a question of which one are you appending to. if it is unsorted, wouldn't be harder to larger run sizes. You can have something that's reversely sorted, which basically means each run only has one single record. It doesn't matter because the next run is going to double the size of each run is going to double. The number of runs is going to be halved. That is the whole idea of the n log n mechanism. Is each run itself will be n, but the number of times you have to split and merge will be the log of n. Yep. So I'm glad some of you brought up merge sort. It doesn't quite fit into what we want to talk about here, which is recursion, even though it can be, I would say, coerced into a recursive mechanism. It is much better off if it is not done recursively. So in this case, the recursive version requires everything to be stored in memory, and that sort of defeats the whole purpose of merge sort. But on the other hand, a binary search tree, can certainly, is a very good example of a self-similar problem, because each subtree of a binary search tree is by itself a binary search tree. So the mechanism of finding a number, a value within a search tree, can be recursively applied. Factorial is a self-similar problem. It doesn't have any structure by itself. It is not a tree. It is not a bunch of folders. It is not an array. We are just talking about numerical values. But to compute the factorial of a particular positive integer, the self-similar approach can be used. Now, it doesn't make it a more efficient way to do things. It just makes it a different way of looking at something and coming up with a solution. Fibonacci is the same way. F of n is f of n minus 1 plus f of n minus 2 until you get to, I think, when n is less than 2. So when n is less than 2, you just return whatever n is. So f of 0 is 0, f of 1 is 1, and then for everything else, you can do it recursively. It doesn't mean that implementation is the quickest way to get to the sequence of Fibonacci numbers. In fact, it's a very wasteful way, to compute Fibonacci. But it does illustrate that it can be done in a recursive way. All right. So, but we can also look at some problems that by its very nature doesn't seem to be recursive, but we can coerce it into something that is recursive. So I illustrated something last time already. You're looking at string compare. You can do the same thing with summing all the items in an array. Even a linear search algorithm using an array of unsorted items, that can also be done in a recursive way. Well, since we are talking about this, might as well go ahead and take a look at linear search when an array is not sorted at all, and how we can do it recursively. So I'm just going to give you a quick example of that. All right, so here's a mousepad, which is just an editor. All right, so we want to do a linear search. So typically, when you do a linear search, you have a subroutine like this, and you'll be given with an array of items. So we'll just say that we have an array of integers. So here's an integer array, which is in C and C++. An array is no different than a pointer when you're passing it. And then you also need to indicate the number of items in the array, because unlike other programming languages, the array itself, or the pointer, does not tell you the number of items in an array. So the typical way to do this is to go through, when the array is not sorted, is you have to do a linear search, and then you start from the beginning. I mean, you can start with the end too and work your way to the beginning, but typically people just kind of don't do it that way. So we will have unsigned I as an index, and then what you do is you have a while loop that says, okay, we have to initialize I first, so I is going to be initialized to 0. And then we have a loop, and in the only thing we do in the loop is to increase the index itself, which is ++ I. And the only reason why we want to stay in the loop is, 1, we have not found what we are here to look for, which means we need another parameter, which is the key that we're looking for, and that's why it is k. So as long as I still have more items in the array to look, and k is not found at this point, I want to increment the index and look again. Set I equals to well, there are interesting ways to do this, without using a linear search. Well, not linear as in this, but we can talk about that in just a little bit. It's not exactly random. You can use large prime numbers to help you kind of step through the whole thing, and it would seem like a random order, but it's not. Anyway, we're going to say I has to be less than n, okay? Because if I is n already, then the index is already out of bound, and we should get out of the loop. And then the second condition that we also need to stay in the loop is by the time we are at this point, by the time we are inside these parentheses, we already know that I is less than n, and because I started off with 0, so I is a valid index. So now we can say p of I does not equal to k, because if it does equal to k, then we should get out of the loop. So now, if I want to return a value to indicate whether k, the key is found or not, what do I do? What is the clue that tells me that yes, I have just found a value? Yeah, we're not going to return I, because the idea is we're supposed to return a Boolean, of whether it is found or not. That is close, Jonathan. That is close, because what if I is already out of bound? Now, if I is out of bound, there is a very slight chance that it just so happens, if you look at the thing that is right past the end of the array, its value, when interpreted as an integer, may be exactly the same as k. So that may not be the best way to conclude either. One is true, and we don't want to use a constant to return true all the time. What Armand is suggesting is close to the solution, but you don't want to utilize I as an index unless you already know it is within the range of proper indexes. But if you know it is within the range of proper indexes, don't you think that you have found the value that you have been looking for? Because the only way for this loop to exit when I is not less than n is everything in the array is not k. So what we want to do, pretty close, just need a negation. You just need a negation. Wait, hold on a second. No, Armand is absolutely correct. We don't need a negation, because when I is less than n, that means we exited the loop because of because the not equal part is false, which means we just found something that is the same as k. So Armand is correct. Okay, I just put in an extra negation unnecessarily. There we go. That'll work too. Double negation. I like that. All right. So this is kind of like a typical way for people to do linear search, but I would argue and say that you can do this recursively, and there are two ways to do this recursively. One way is to resemble what we did last time. Basically, we look at the first thing. We look at n first. Okay, if n is greater than 0. Then we just go like, okay, we have at least one element here, and we'll just go ahead and compare whatever p is pointing to with k. If it is the same, cool, we'll just return true. If not, guess what? We'll look at the rest of the array, and we'll call the same subroutine to look for that. So let's go ahead and write the recursive version, the first recursive version. Same prototype, because if it's not the same prototype, then it's not going to be as good as an argument and say that we can look at this recursively or not recursively. All right, so in this case, in the case of a recursion, it's not going to have a loop. Okay, so there's no while loop here. If there's no while loop, so the decision making has to be done using a conditional statement, an if then else, conventionally speaking. But every time you use if then else, there is a pretty good chance that you can also use a ternary expression. So we're going to use a ternary expression, so we say return right away. Okay, we are not going to use stinking conditional statements. So now the question is, man, how do we think about this? Well, as I said, think about the simple cases first. Okay, so the simplest case is when n equals to 0. When n equals to 0, I'm going to return false right away. Because when the array is empty and you're asking me is k in it, the answer is quite obvious, no. Okay, so, and this is why ternary expressions are they are right associative, because this makes the if then else possible. So you basically have a else if type of branching when you are specifying ternary expressions. So if n does not equal to 0, but n is an unsigned, so if it is not 0, it has to be at least 1. So when n is at least 1, I can at least compare the first element of this array with k. So I'm going to look at p of, okay, it depends on which way you prefer. Okay, we can do this. This is one way to specify it, and the other way to specify is this. They mean exactly the same thing. It's just eye candy. Okay, so it's basically your preference. Do you want to look at p as a pointer, or do you want to look at p as an array? They mean exactly the same thing in C and C++. But either way, I'm going to look at it as an array in this case. So if it is indeed the same, then I can just go ahead and say, yep, we just found it. Yes, 1. Okay, I don't have to specify a 1 here. Anything other than 0 would do. So 2, 3, 100, depending on the width of an int, you can specify anything that is non-zero that will fit into the width of int in this case. So the last case is the only case where, oh man, darn it, n is not 0, which means it is greater than 0. And the first element of the array does not contain the key that we are looking for. So what are we going to do? We're going to have to find someone who knows how to find a value in an array. And who would that be? Name one subroutine that can return whether a particular value k is in the array or not. Yep, lin search. So that's why we are just going to say, I guess we'll just call lin search. But this time the array is advanced by 1, and then the number of elements is reduced by 1, but it's going to be the same value that we are searching for. Is that okay? Now, for those of you who do not like to look at pointer arithmetics and say, pointer arithmetics has no place in this particular program because we are looking at p as an array. Fine, okay? If that is how you want to look at things, we can look at p as an array. So then we're going to change this to, it is the address of p bracket 1. It means exactly the same thing as what I had earlier, except this time I'm looking at p as an array instead of a pointer. Once again, eye candy. Okay, this is all just eye candy, depending on whether you want to look at p as a pointer or whether you want to look at p as an array. Typo in recursive call. Okay, lin search without the s, right? Yep, there we go. All right, so are we kind of getting the hang of how to turn something that usually is not done in a recursive way, and we can just kind of turn it into something that's recursive, sort of. Okay, so the key is laziness. Okay, I hate to use that word. Maybe we can just use the word optimistic. Okay, so it's not greedy, it's not lazy, it is optimistic. There you go. So it is being optimistic. It's like, okay, if this n is a 0, woohoo, I don't have anything to do. Cool. Or if it is not 0, but the first element turned out to be the one thing that I'm looking for, cool. Oh man, then we worry about the case where, oh man, it's not an empty array and the first item is not what I'm looking for. Then we look for excuses to have somebody else to do the job. basically we say, well, we'll just kind of cut off the first item that we know is not the value that we're looking for, look at the rest as an array, and then give it to somebody else to solve this problem. That's basically what recursion is. Alright, so the text channel says mainly deals with finding base case and transforming the main loop into a self-call. Yes. But it is about how you look at things. Okay, so in the end, it really boils down to how you look at an array in this case. Now, I did say that this is only one way to do it, so there's another way to do this recursively. And so this other way is interesting in its own way. So I'm going to give you that too. So we have P as an array, unsigned n, which is the number of elements, and then k represents the value that we are searching for. Now, obviously, in this case, I have done something really bad because I really should have used const int the whole time. Because this is a search algorithm, it's not supposed to change the elements inside the array. So typically speaking, you really want to add const so that if you accidentally do something, in the program and you change the elements, the compiler will bark at you and go like, hey, you're not supposed to do that. But that's, once again, is kind of eye candy. Okay, so alright, so this time what we'll do is we're going to break the array in two, but not using the technique that we just talked about earlier. Okay, so we're going to say return again. Once again, it is using ternary operations. Okay, so we'll say if n equals to 0, then we say nope, there's no way we can find it here because the array is empty. And then the next one is still saying, okay, if the array is non-empty, let's see. So the next one is to look at n to see if it is 1. If it is 1, then we're going to just return p bracket 0 equals k. Because in this case, the array only has one single element, right? So if the array has one single element, just by comparing k with that one element of the array would be the conclusion of whether the array has that value or not. Now, the interesting thing about this one is it will break the array not by 1 and then the rest. It will break it into approximately 1/2 and 1/2. So this time we're going to do a lean search, okay? And we'll start with p, and this time we're going to divide n by 2 and looking for k, and then we'll have an OR on this side and say lean search again. But this time it's going to be about in the middle of the entire array. So this is going to be p plus n divided by 2, the whole thing. Let me think. Yep, that would do it. And then we also have to, the number of elements in this case will be n minus n divided by 2. And we're searching for k again, right there. There we go. Okay. So this is another way of breaking down an array into smaller components. But instead of just taking the first thing out and then say the rest is also an array and just pass it on, this time I'm breaking the array into two approximately equal halves. Okay, there are several ways to do this, depending on whether n is even or not. If for some people they prefer to look at this as n divided by 2 and then minus 1 over here, and then you can just put another minus 1 here because that would be the start index. And then over here you would also have a minus 1 over here. Let me see. Let me see if that makes sense or not. Nope, that does not make sense. Never mind. I just self-checked myself and go like, no, that does not make sense. Tech, go away. Nope, the original one is fine. The original one is fine. Yep, it's all one single return statement. That is the cool thing that a ternary expression can buy you, is you can have, depending on the complexity, okay, depending on the complexity of the recursion, you can potentially just have one single return and use ternary expressions or nested ternary expressions in this case to actually specify the logic of everything that you need to do. Yep, exactly. Exactly. That one single, because we have one statement, we have one expression. Now, this expression is complex, but nonetheless, it is just one single expression. It has two ternary expressions. One is nested within the other one. And once again, the natural association of a ternary expression is right associative. So that means, what that means is this entire thing is basically a ternary expression that is nested as the else of the first ternary expression or the outer ternary expression. I don't need a nested extra pairs of parentheses because it's already right associative. Can you say that expression? It's just a if then else, right? If n equals to 0, then 0 becomes the result. Otherwise, if n equals to 1, then p bracket 0 equals k becomes the value of the expression. Otherwise, it becomes the disjunction of lin search p n divided by 2k and lin search p plus n divided by 2 n minus n divided by 2k. There you go. I've been waiting for many years for someone to turn a C or C++ program into a rap song. And so far, I have not found anyone doing it. And I'm not going to do it. Absolutely no way I'm going to do it. But I just thought somebody might have the talent to do that, and that would be pretty funny. Yeah. What does that disjunction do? Very good. Good question. Well, because this one is actually searching more or less the first half of the array. So if the first half contains k already, I go like, I don't need to search the second half because I found it already. But if the first half does not have it, then I'm going to have to search the second half because I still have a chance that the value k is in the second half of the array from the perspective of this invocation. So that's why there's a disjunction, because it's whether the entire p from my perspective has k or not can be, it may be in the first half of the array, it may be in the second half of the array, and the proper logical operator is the OR in this case. Yep, it just yes, that's what it's going to do. Now, the nice thing about this, okay, there are certain things that's nice about this approach versus the first one. The first one is going to take up stack space that is proportional to the length of the array itself. The second one is going to take up stack space proportional to the log of the length of the array. So that's why the second approach is a little bit more, I hate to say it, pragmatic, because it's not. But compared to the first approach, it is a little bit more pragmatic, because if you have an array that has, I don't know, let's say 1 million items, the first approach is going to have 1 million call frames. It's not 1 million bytes, it's 1 million call frames. So if you're taking CISP440 from me, you kind of know what a frame is. So a frame contains, basically all the parameters, all the local variables, and some of the registers and so on, depending on the architecture. Okay, some architectures throws all kinds of junk into the call frame, so it can get pretty big. Other architectures may be a little bit more kind of frugal in terms of how they what they put into a call frame, but nonetheless, you're talking about, in this case, let's count. Okay, even with a 32-bit architecture, this is 4 bytes. This is also 4 bytes. And then you have the return address, which is another 4 bytes, right? So at a minimum, okay, each call frame is going to take up 16 bytes. So if you have when you have 1,000 recursive calls, then you're going to take up 16 megabytes in the first approach. The second approach, on the other hand, is only proportional to the log 2 of the length of the array. So when you look at a million, okay, 1 million is approximately 2 to the power of 20. So you're looking at 20 levels instead of 1 million levels deep in terms of recursion. So the second approach is not, it's still not a very nice or efficient approach, but at least from the perspective of how we are using the stack or how deep the recursion is going to go, the second approach is only going to use up like 20 levels of call frames, whereas the first approach is going to take up 1 million levels of call frames. So it does make a huge difference when it comes to how much space, stack space is consumed, depending on whether it's the first approach or the second approach. Well, your stack size depends a lot on your operating system. In some operating system like Linux, you can actually reconfigure these how much stack space is allocated to each process. So there's a certain wiggle room, but it would still be a very bad idea to have one single linear search algorithm to take up 16 megabytes. That is just not a very good use of system resources. I'll put it at least that way. Okay, so but are we understanding the approach of these three different implementations of exactly the same thing? It's just linear search. Okay, one of the simplest algorithm that you learn from CISP440. But in CISP440, they only talk about the first approach. If it's me, I would have talked about the second approach too, because I think recursion is extremely important to introduce early on so that people can. So this forces me to talk about how things are actually stored inside the computer. Okay, and I think it is important for people to understand that even as early as CISP440, even if they don't understand what is the stack. But we are not going to call it a stack, but we have LIFO. Okay, this is a LIFO way of stashing things in a computer. All right. So, any questions at this point about how we turn something that's usually simple like this into something that is a little bit convoluted, but nonetheless it reflects the concept of recursion? Okay. No questions from Jonathan W. How about the rest of the class? All right. I think the breaking of the algorithm into smaller repeatable steps is a bit hard. It's a perspective. It really is a perspective. You're basically looking at a problem and you're asking for at least the base cases first. So the base cases in this case would be fairly easy to think. In other words, we're looking at it from a kind of optimistic perspective, right? It's kind of like asking, okay, under what circumstances do I not have much work to do? And that will handle all the simple cases. So when all of those cases do not apply, then we have to think about, oh, okay, so we cannot just make a conclusion right away, but can I cast the problem into a subproblem that has similarity to the problem that I'm given with? That really is the question to answer when you are trying to think in a recursive way. Yeah, it is a perspective kind of issue, but it's not a kind like object-oriented programming versus procedural programming, because those two are, even though it is a perspective shift, there is a bridge concept in between called ADT, or abstract data type. So object-oriented programming is really a progression from abstract data type, which is basically just go like, okay, instead of accessing members of a structure or a class, an object, will have methods. Okay, we'll have subroutines to do that. So the only difference is whether the method or the subroutine belongs to the object, or it is its own subroutine that you have to call, and then you have to supply the object that you want to work on explicitly or not. So at that point, it's kind of eye candy. And obviously there are other things where eye candy does not quite apply, such as abstract methods. Those are a little bit different. I look at abstract method as sticky method. Okay, it's it's stuck not to the class, but it's stuck to the object itself. So it is kind of like a sticky thing. It's stuck to the object, and that's how I look at abstract methods. Anyway, I'm digressing away from what we are here to talk about. All right. So getting back to Joplin. So we got self-similar problems, linear search in an array, binary search tree. Now, binary search is another example of applying the concept of recursion. How many people do not know about what is binary search? Not binary search tree, but binary search, which applies to an array that is sorted. Okay, I don't see anyone indicating that. So I'm going to assume everybody know about what is binary search. Okay. So, oh, right. Okay. So binary search is actually a very interesting concept too, because it really illustrates the idea of a log n type of algorithm. And the idea is you have an array, okay, and it is already sorted. And you want to find whether a particular value is in the array or not. So instead of starting from the beginning or starting from the end, you start from the middle. So you pull whatever elements in the middle and you compare that to the key and go like, no, not what I'm looking for. But because it can be less than or it can be greater than, so either way, you're going to be able to rule out 1/2 of the entire array and say the key, whatever value I'm looking for, cannot be in that portion of this array. So what are you left with? A smaller array. So when you look at the smaller array and you go like, okay, now we need to find this value in this smaller array, that's recursion right there. Because that small array is an array by itself, and then you can just apply the same technique, And that would be the first, I think it's one of the first algorithms that you would encounter in CISP, say 300, where the concept itself is extremely recursive, except the implementation may not look recursive, but the concept is very recursive. We take one element, we compare, and then we only have 1/2 of the array that may contain the value that we are looking for. The other half is gone, so then we just reapply the same technique to whatever is left of that array. All right, so let's take a look at some other interesting algorithms that are also usually known to be recursive. So we're going to take a look at Pascal's triangle, and this one is not the right version. All right, so Pascal's triangle is also closely related with, it's the same because I forgot to republish my content. All right, so where is that? There we go. Yep, everything is sort of command line to me. Alright, so now it is, okay, now it's better. The only change is this here, whether we are comparing to a 1 or a 0. So if you remember Pascal's identity, it is about combinations, okay? So instead of using combinations, I just call it Pascal. Okay, so Pascal is combination. Pascal is combination. So this is the recursive way to find combination. And let me see. I think it is C choose R in this case, which is kind of having the parameter reversed. But the idea is it is recursive because you have Pascal being used here, and then you have Pascal being used here. And this is one of the things when we talked about Pascal's identity, we basically express combination in combination itself. So that's also a case where we kind of discover that in addition to factorial having a self-similar quote-unquote recursive nature, combination actually has that nature as well. So it's kind of cool, but it's very numerical. The third one that I want to talk about is the Tower of Hanoi. So the Tower of Hanoi is an interesting problem. I think I cannot make the assumption that everybody in this class knows about um, the problem of the Tower of Hanoi. So in Tower of Hanoi, you have basically three poles. Okay, let me go to Wikipedia. So let's search for Tower of Hanoi. And this is the Wikipedia page. And it's nice in a way because it has an animation. Oh, great. I'm going to have to make a donation. I think I actually made donations to Wikipedia. So, all right. So the problem starts with this, okay? And your objective is to move all the disks all the way to the third pole over here. And most people think, oh, that's easy peasy, right? We just lift the entire stack up and then drop it into the third pole and we're done. Well, okay, we got some rules, okay? One of the rules is you can only move one disk at a time. Okay, well, that doesn't seem too hard. I'll just move these disks over here, and the smallest one will go to the bottom, the second smallest will go on top of that until this entire thing, the entire stack, is reversed on the second pole, and then we'll move all of those disks in the same manner onto the third pole. We're done. Okay, let me tell you another restriction. You cannot put a larger disk on top of a smaller disk. Now the problem gets a little bit harder, doesn't it? Okay, because now we have three rules. You can only move one disk at a time, and you can only put a smaller disk on top of a larger disk. And then the idea is we want to move all the disks from the leftmost pole to the rightmost pole over here. So this problem has a has a history. It's kind of a very interesting history too. So if you read the history, I think the original problem has 64 disks, and supposedly the monk is supposed to move the 64 disks, using those rules that I just talked about, from the leftmost pole to the rightmost pole. And also, I think supposedly, once this is all done, it will be the end of the world, if I remember correctly. So the question is, well, I think it was 64 disks in the original problem. I could be wrong. Let me see. Yep, 64 disks. So with 64 disks, most people look at it and go like, nah, that cannot take too long. I mean, it will be the end of the world soon enough. Well, as it turns out, it's not like that, because it is actually exponential. The number of moves you need to do is exponential to relative to the number of disks. So with 64 disks, this is the number of times you have to move a disk. It's 2 to the power of 64 minus 1. So even if you can move a disk per second, it will take 585 billion years to finish. Now the entire universe is only it's 16 billion years old or something like that. Yeah, it's definitely not within the hundreds of billions of years yet. So I'm not too worried about the end of the world if this is how the end of the world is determined. Because I think the sun is going to expand and engulf the earth first before anything else happens. All right. Okay, so Amon brings up an interesting point. Is it going to take up a lot of memory? That's the question. Okay, how much memory is this going to take? So the idea is it's not going to be any more than 64 levels of calls. So even if each level of call takes up, I don't know, let's call that 64 bytes. So you're still looking at 64 bytes times 64, which is not a really big number when it comes to the memory footprint. Okay, this is for the stack. So the stack space footprint is not all that bad, but it is an exponential algorithm. In other words, the amount of time it takes to execute is exponential to the number of disks. Is that okay? All right. So actually, I use this. Sometimes I use this as an example in my assembly programming class, and I would sometimes, and sometimes the students would implement the Tower of Hanoi using assembly language, and the entire program would fit in 256 bytes. Um, in other words, the logic is not complex. Okay. So let's take a look at the solution of the Tower of Hanoi problem, and then we'll try to, because I think it's a very good illustration of how to solve problems recursively. And obviously, this kind of stuff is hard to ask questions about. Okay, just because I'm introducing a way of looking at things. It's really hard to ask questions. To see if people understand how to look at things from a certain perspective. All right, so we have Hanoi. Okay, Hanoi. All right, so let me see. It needs several parameters. So it needs the poles. Okay, so we have the leftmost pole, the mid pole, and also the right pole. And then each one basically has a number of disks in it. And okay, so now we ask the question, how do we do this? So once again, we want to think of the simplest case first, right? So the simplest case is if there's only one disk to move, we know how to do it. I actually take it back here. So there's a from post. Okay, we'll call this from. There is a via pole, and there is a to pole. So each one is an integer, 0, 1, or 2. We can say 0 means the leftmost pole, 1 means the middle pole, and then 2 means the right pole in the configuration. And we also have the number of disks to move. So then we have unsigned n as the number of disks to move. All right. So now we need to figure out what do we need to do. So once again, we are being optimistic and go like, well, let's think about the cases where there's nothing to do. Okay. So obviously, when n equals to 0, there's nothing to do. Okay, because there are no disks that we need to move. Pretty easy peasy. All right. So the next case we're going to look for is going to be n equals to 1. Because when n equals to 1, we don't need to use the via pole. We can just move directly from the from post pole to the to pole. So we'll just kind of we can use a printf statement here if you want to. So we can use a printf, and we just say move disk from pole %d to pole %d. Now, if you don't know how to use printf, it's not a big deal. This is just a formatted output, so that we can say, this which pole is we are moving from, and which pole we are moving to, and it is already done. All right. So now we can end up with a case where n does not equal to 0 and n does not equal to 1. So when n does not equal to 0 and when n does not equal to 1, maybe we need to use recursion in this case. Okay, so the idea is to try to look at this problem, and break it down into a subproblem. Okay, so the subproblem is to think of it as, let's move all but one disk from the from pole to the via pole. Okay, so I'm just going to comment here first. Okay, so we'll say move n minus 1 disks from the from pole to the via pole using the to pole, and then we can move the one disk left. Okay, so move the one remaining disk from the from pole to the to pole, And then what we'll do is to move the n-1 disks from the via pole through the from pole to the post pole. So we will say move n-1 disks from the via pole to the to pole using the from pole. Okay, so let me double check and make sure that I'm making sense here. Move n-1 disks from the from pole to the via pole using the to pole. So I'm going to put quotes, just so that we can identify those are the identifiers of the poles. And then we'll move one disk from the from pole, in quotes, to the to pole, which is also going to be quoted. And then move n-1 disks from the via pole to the to pole using the from pole. Okay, so that looks good to me. Absolutely. There we go. I think you guys can see at the bottom now, right? Let me move. There we go. All right. What does that mean, right? Okay, so a picture really helps. So let's go back to the picture, which is here, and scroll back to the diagram. So what we're going to do is to say, okay, we need to move all of these disks from here to here. But we can use the one in the middle kind of like a temporary variable, so we can kind of use it to help us out, right? So we look at this situation and we ask, okay, I'm trying to be optimistic, in other words, greedy, or lazy. We are asking, is the number of disks that I need to move being 0? No, because we got how many here? We got, is it 8? Yeah, it looks like 8 disks in this case. Yep, it says right here with 8 disks. Okay, fine. So is it one disk? I mean, that's a stupid question because I just said we got 8 disks. No, it's not just one single disk. Okay. So what we're going to do is we're going to say, well, let's just say that we have an algorithm that can help us move a bunch of disks. And this magical algorithm, I would use this magical algorithm and say, move the top 7 disks over here from the from pole. This is the from pole. I will move the top 7 one into this middle pole over here, but using the last pole, the to pole, as quote unquote the temporary pole. Okay, and you guys would go like, but we don't have an algorithm like that. I would go like, just pretend, just pretend that we have this magical, algorithm that can do it. Okay, fine. If tech wants to fantasize, such an algorithm does exist, fine. We'll entertain him, and just say that such an algorithm exists. So now that I have 7 of the 8 disks, sitting in the middle pole with nothing on the to pole. Okay. So I know how to move that one disk, which is the only disk left from the from pole, from here to here. Cool. And then I would basically go to the same magical algorithm and say, okay, we still got 7 disks in this pole here, and this time we're gonna have to move those 7 disks from this pole to this pole over here, but using this pole, which would be empty at that time, as the temporary pole. You go like, so aren't you double fantasizing now? Well, it's not double fantasizing. It is still one single fantasy algorithm that can do it. It's just kind of imagine that we have this super duper algorithm that can do it. Then you go like, okay, fine. Then we end up with what? We end up with the code that we have here. So you look at this code here and you go like, but isn't that what this subroutine is supposed to do? Okay, you specify which pole you're using to copy from, which pole you're trying to copy to the destination, and which pole is quote unquote the temporary pole, and then you specify the number of disks that you want to move. Oh, so this is the real magical moment, is to understand that fantasy, that fantasy algorithm that I was talking about is the very same subroutine that I'm trying to write at this point. Okay, because that's the purpose of this subroutine. So we're gonna say, oh, okay, that means we can call Hanoi here, But you have to be careful what you're passing as the parameters, because we are copying from the from pole. So from is the first parameter. But you have to be careful with the other two, because we are now copying to the via. So that means the next one is 2, and then we have via, and then the number of disks that we're copying, moving, is n minus 1. And so the last one is going to be easy too, right? Because this one is just going to be Hanoi again. And where we're copying from is the via pole from the perspective of this invocation of Hanoi. Which one are we using as the via? It will be the from pole. And where do we want the disk to end up at? It will be the to pole. And then the number of disks that we need to move is also n minus 1 in this case. So what is left at this point is the one in between, okay, which is this one over here. This one can also be done using the Tower of Hanoi, because we know how to do what to do when we only have one disk to move. So we'll go ahead and recursively call Hanoi. I mean, you don't have to do it that way. When you only have one disk to move, you can just go ahead and say, okay, I'm moving from here to here. But I'm just going to do this entirely using recursion, even when it's not necessary. So this one is moving from the from using the via to the to, but since there's only one disk to move, there's no need to use the via. So the via is still here as a parameter, but I'm not going to use it. There's no need to use it. And now we have the algorithm. This is the algorithm to solve the Tower of Hanoi. It will give you the sequence of where are you moving a disk. In other words, when you run this code, you end up with a whole bunch of statements that will tell you move a disk from which pole to which pole. Okay, pole 0 is the leftmost, pole 1 is the middle, and then pole 2 is the rightmost. So in main, okay, the caller of Hanoi, okay, so if you want to complete this program, your main is going to look like this. Okay, all it is Hanoi, and assuming that 0, 1, and 2 is how we want to identify the poles. So we have 0, 1, and 2. There's no need to use just 0, 1, and 2. If you want to use 10, 20, and 30, it doesn't matter, because all we are trying to do is to use 3 unique integers to identify which one is the from pole, which one is the via pole, and which one is the to pole. Okay, so it's just an identifier. As long as those values are distinct, we are fine. And then you can specify the number of disks that you want to move. So we can specify 8 here. And then what this particular program is going to end up doing is it will just give you a bunch of these move disk from pole blah to pole blah. Each time you're moving a single disk, whatever is on top of that pole, that's the one disk that you're moving. And it would just be lines and lines and lines of instructions like this. So do we have any questions about how I approached the Tower of Hanoi algorithm? Because it's not about the algorithm itself. You can easily look it up and find the Tower of Hanoi algorithm. It is about the approach, how we make that assumption and say, let's just fantasize and just say that there's a magical algorithm that can take care of the n minus 1 disks. That is the key. Now, we have encountered concepts like this already in this class. That would be the assumption part of proof by induction. We basically make the assumption of the theorem is true for cases up to k minus 1. Now let's work with the case with the value being k. Don't you have to come up with a generic enough subroutine that it can be reused for other purposes like this like in this example? So it's about breaking a problem into a subproblem. In other words, when I wrote this line of comment, I was just making an assumption. It's like, okay, let's assume that we can do this, okay? And then later on, we recognized that what I'm trying to do in the comment is exactly what Hanoi itself is supposed to do. And therefore, we can just do it recursively. So once again, the technique is really to recognize that a larger problem can be broken down into smaller problems, and then the nature of each smaller problem is the same as the larger problem itself. It's just that the size of the problem is smaller. Now, sometimes it's smaller by one, sometimes it's halved. You know, that part is it kind of depends on what problem you're trying to solve. But the idea is the same. You're breaking a larger problem into smaller problems, and then each smaller problem has exactly the same feel, the same characteristic as the original problem that you're trying to solve. So that is the technique of applying recursion. Oh, we're running out of time. Okay, so time runs really fast when you're talking about something that's fun. So I'm gonna let you guys go. What we're gonna do on Monday. Oh, okay. So let's take a look. So this is so Tower of Hanoi is specified here. Yeah, I changed the position of and. Instead of being the last argument, it's the first one. Now, frankly, I actually did not read my own notes when I came up with the algorithm on this side. And trust me, I don't really study that hard. Okay, yes, I would make a very bad student. But the whole thing, basically was just me, coming up with the algorithm in my head as I talked about it. So the nice thing about this is, okay, you can always say, but Tech, you're just being lazy and not prep for your classes. But the nice thing about this is I can actually show you how I came up with this algorithm. What the thought processes are to come up with the algorithm itself, instead of just reading it from a book, right? So we have deleting from a folder directory. Deleting a directory. How you basically you need to go depth first search. Remove the last item first, and so on. So this part, all of this stuff here is really just looking at things from a certain perspective. So when we get back to the modules, this is all under time complexity, by the way. Okay, so if you look at the module, it is all under big O, big omega, and big theta, because the next one is to talk about the categories of time complexity. And the interesting thing is there is a way, if you can specify an algorithm recursively, and you can say, I'm going to break the original problem into this many pieces, okay, and then you can relate the summation of all the pieces as a percentage of the original piece. And then you can also specify, okay, in order to combine these sub-solutions, we need this much time. So as long as you can express the algorithm in a recursive way that fits into this particular constraint, then it is actually very easy to determine the time complexity of the algorithm. That's why that's why I was talking about, okay, let's look at an algorithm that can be done without using recursion, because once we cast the solution of the problem into a recursive solution, then we can use a very special and kind of handy way to analyze the time complexity of the algorithm. So it becomes kind of much more mechanical. It's not like oh, this algorithm is special in this way, this algorithm is special in this way, and every single one needs its own reasoning to find out the time complexity. So instead of doing that, we can now have a template of things and go like, okay, if this number is larger than this number but that number is less than that number, it falls into this category. If it is another case, it falls into this category. If it's another case, it falls into this category. So it makes it very easy to apply a template-based approach to find out the time complexity of how to solve some specific problems. So that's what we're going to talk about on next Monday, is categories of time complexity. I didn't quite finish reading the entire recursive definitions and algorithms, but the rest of that really is kind of a way of looking at things. So it's not going to add a whole lot more if I were to kind of finish the reading of the entire module in this case. So next time we're going to start with categories of time complexity. So that's what we're going to do. Will we have a homework about converting a function to recursion? I have not planned it out yet. So for now, let's focus on that cousin, the cousin homework assignment. The cousin, prologue in many ways is recursive too. A lot of the predicates that you're going to write for this program is recursive. Okay, there's a base case. The base case is easy to determine, true or false. But then, if the base case doesn't fit, then you're gonna have to go for the recursive case, so that you're reducing n or m by 1, for instance. Okay, for each recursive invocation of the same predicate. So there you go. Alrighty, so you guys have a good day. Have a nice weekend. And if you have any questions about the homework, just go ahead and ping me. I'll be online for the next hour or so. That's basically my office hour. And if not, just go ahead and find me during my office hour, or just leave a message on Discord and I'll get back to you. So you guys all have a good day, and I am signing out, but I will be online.